I'm Ryan Stortz, and this is Swift reversing. My talk is broken into 3 parts. I have an introduction to Swift, a discussion of my methodology for my research, and then the actual results from my research. So Swift is supposed to be Apple's new sexy language for the future. Just like everything Apple does, it is more ceremony than substance in the first release. If you remember the iPad or the iPhone or the iWatch or the Apple TV, Swift is right there. But Swift is meant to take over for Objective-C, and I think all of us can get behind that. In a funny twist of fate, I guess, to make myself more grandiose. Swift was open source back in December after I did a lot of my research and right in the middle of the OpenCFP process. So my work actually cheated a little bit, and now I use some of the ABI documents because what's the point of presenting about what I had done and failed at, or not failed at, but done in an incomplete fashion when I have the answers and I can give them to you. I'll do the reading for you. So Swift is also technically available for Linux as well, but OS X, but so was Objective-C. And who has seen an Objective-C Linux app before? No one. And I guess now Mac rumors as of yesterday says Google is considering adopting Swift for Android. So exciting times, I guess. Swift is pretty expressive. You can do atrocities like this one. This is Mozart. Down here we have the output at the bottom. So, I was told that I had to change this to, instead of using the heart, it should have been a love hotel. But I had the slide down already. So Swift, it's a fairly high-level language. But it's meant to be fast, so it's actually considered a systems programming language, or close to it. So all of this Noah's Ark runs super fast because it's compiled machine code. And this talk is about reversing that machine code back to, it's really reversing it back to C++ or to C because X-rays and whatnot don't really handle Swift, and there'll be a lot of that later. So Swift is considered a modern language. I'm not really certain what modern language means, but I think it means it was designed after Mudge invented the buffer overflow or after Java. It has all of the features you'd expect. As a reverse engineer, the more closures and generics could be problematic, and that kind of concerned me going in. But you get first-class functions. You have iterators. Map and filter, air handling. Swift makes heavy use of these optionals, which I thought would add a lot of noise to disassembly, and I'll get to that. But first I wanted to talk a little bit about the compiler architecture. So I got into Swift reversing because I was doing a lot of, I've done a lot of reverse engineering in the past, but I was also doing a lot of LLVM, IR-based transforms and analyses, and Swift kind of, interests me. I went to the LLVM dev meeting and got surrounded by backpack people. There was a talk about Swift and SIL, and I'm like, okay, this is kind of cool. SIL kind of lets me do these things that weren't possible. So I'm going to take a small segue here and talk about the compiler architecture. Small children can turn away. So both Clang and Swift are built on top of LLVM. In Rust and a million other languages as well. And this is pretty powerful. So Clang actually mostly emits straight into LLVM IR. And its optimizations are done in the LLVM layer, not necessarily in the Clang front-end layer. And this is neat because a lot of languages like Swift and Rust can take advantage of this optimization and they can build on top of it. So Swift actually introduced this new intermediate language, SIL, and they do their analysis and optimization there, and then also in the IR level. So LVM, or Clang does it here, and Swift does it there, which, you know, is interesting as a reverse engineer. I was asked to give a walkthrough of a slide PowerPoint-based compiler. So we have our Noah.Swift here, and that gets compiled into a standard AST. I thought it was hilarious that my terminal printed out all the emojis. That gets emitted into SIL. This is where the first level of optimization happens. SIL is, one level higher abstraction than LLVM-IR, and it has a full awareness of the the Swift type system. So if you've done analysis on IR, you're familiar with the problem of devirtualizing virtual function calls and figuring out your types, and a lot of things that compile, you have to deal with to do optimization or just analysis. And Swift doesn't have to deal with that. They have much higher level constructs. They have their method lookup is an opcode that you can use. So that's amazing. So this higher level of abstraction allows Swift to optimize their IR much more freely, and that's where you get your speed from, your safety. That goes down to LLVM-IR. It's mostly just noise. You're not expected to read it. And then finally machine code, and I apologize for the AT&T syntax. In this presentation that I went to, Latner had a slide on SIL and SILGen, where since Swift has so many ways to create closures, and SIL has implemented this alloc box, which declares variables, closures, classes, all on the heap. It allocates everything on the heap. But that would be slow and awful and be basically just Java. So SIL has these guaranteed optimizations that you cannot turn off to bring some of these variables onto the stack and more performant things. So it actually does escape analysis on the variable to see if what scope it's available for. And if it never leaves the stack, it's going to bring it to the stack. And there's some weird cases where it brings it to the data segment, but that's mostly involved in Swift once. So annoyingly, this means that there are 2 or 3 different representations for every bit of code based on how the compiler tried to optimize that specific call or call say or whatever. So I was a little frustrated with that and worried about how to deal with that. So that's my little segue on the compiler. On the left here is a hexarrays output of Swift that corresponds with the Noah's Ark. So how can we get the thing on the left to look more like the thing on the right, or at least have any idea as to what's happening? That leads into my methodology. So on my talk abstract, I promised a systematic approach to reversing a new language or new API. And it mostly starts with things I was confused about going in, but there's a system. It's not just clicking, most of it. So I could probably spend months or years poking at the compiler and its output, trying to get a full grasp of the language, but that's not really going to make any progress. So the research has to be driven by the work, and because of that, the talk will cut out some bits that are more interested in certain subgroups here. So our motivation for this talk will be application pen testing, but really it's about building character, which is what I say when I've been reversing this one firmware for hours and not making any progress and losing track as to what I was even trying to do. It's yes, let's apply more types. So My initial questions focused on 3 areas: the toolchain, the language core, and the ABI. In general, you'd ask more questions about, including stuff about the standard library, but Swift's overlaps pretty significantly with Objective-C, so I wasn't too worried about that. And for the sake of brevity, it's not here. So for the toolchain, what tools are available? Language core, what language core features are going to hinder reverse engineering, and same with ABI. How do they represent classes and calling convention and all that? For each example, I created one or more small projects that encompassed the language feature that I was most worried about, and as small a package as I want. And then looked at, the intermediate output, or language output, and the machine code output, and tried to derive my knowledge from there. Occasionally, I also jump into the compiler source code, but that was rare because it's got like the LLVM source code in it like 3 times. And it got confusing. This is one of my examples. This is my example for class inheritance. I have a class called vehicle. Bicycle inherits from it, tandem inherits from bicycle, or train inherits from vehicle, and there's overridden functions, there's optionals, there's later in this block there's pattern matching. That was one example. Another example is, this is the closure example. This has 2 small closures in it. On the 3rd line, there's the map of numbers where they're multiplying each number by 3. And then in the function body, or in main, there's the mapping of everything to integer, forcing it to unpack the optional. So this actually will crash if you don't get the integers. And from here, I figured out what I'm presenting now. So starting off, we're going to do the Swift toolchain because it's the easiest to start with, and why not? So I started with Google. And the first 9 results were about Swift class string array reversing, and the 10th one was about Taylor Swift reversing female opinion. So there's not a lot out there. There's a Swift compiler, there's Swift, which is a wrapper around the compiler as a REPL, and then Swift to Mango, which ended up being the most useful. For the REPL, it's neat, but it's not all that useful for reverse engineering. What you can do, like I was using it to figure out things about the language, but you're not likely to get the source code of your Swift to then paste into the REPL, or the application you're reversing, and then paste into the REPL and read the code from there. I thought it was awesome that you could just invoke directly into LLVM, and it jits out whatever you type in. In this case, I'm forcing it to unpack a nil optional int, and it's crashing. Swift to Mango ended up being the most useful tool in the official toolchain. It's much like C++ built. It just takes mangled names and demangles them. The big difference is the names here are much more expressive than you get in C++. So you get a lot more type information. You actually get some ownership information encoded in here. This bottom example, you see it's a specialized function where arg1 is dead. Dead means the caller function doesn't care about it anymore. It's up to the callee function to maintain its lifetime. It also has this awesome expand mode, which you're not supposed to read. But it gives you a parse tree of the mangled name, and it makes it to three columns. So there's not much available. Just really Swift to Mango. Class dump, if you're familiar with Objective-C stuff, it doesn't crash on Swift anymore. But it does not really. It doesn't really give you any information. It turns out the class structure of Swift and Objective-C is identical. So it can easily be updated to support Swift. And if it weren't a horrible Objective-C project, I probably would have done that. So next up is the language core. So for the language core, I was concerned with native types, control flow, optionals, and class instantiation. This is built, yeah. So for native types, this is on the slide for native types. Most of them decay into a Swift built-in type, and then those decay into LLVM native types. And on the right, you can see a few of them have decayed gracefully into UTF-8 strings and scalar integers. They don't have all the cruft that you'd expect from like Java wrapping it, where now it has like it's a ref counted integer or constant string. So I was actually surprised that it happily decayed into a UTF-8 string, which turned out very nice because we didn't have to add special handling to it to IDA or hex arrays. So for control flow, in my original questions, I wanted to know if it were message-based or lazy like Haskell. Actually, Dave tweeted my best joke about Haskell, which is reversing it is a ring of hell that Dante didn't quite describe. So I was happy to find that the control flow is what I expected. So up at the top is a pure Swift example. It's very procedural, and it's hex arrays output. In the bottom, you can see that there is a message-based Objective-C message send call, but that's actually only there when you're breaching into Objective-C. So if it's pure Swift, you see none of that, which was very nice. Optional. So I mentioned optionals a few times. For review, optionals are a way of packing the value of an object, of a value or nothing. And you can't access the value without checking to see if it's nothing or not, right? It's a safe way to handle errors. And it's also great for the compiler because it can optimize that. It's nothing ugly like exception-based error handling where control flow can diverge from anywhere and you never know what's happening, and exceptions also in exploitation primitives, and it's also not like NT status where there's a global namespace where you have to make sure your return code is valid, and then you have to do all the horrible NT status things. So optionals, are a great way to handle errors. I have two examples here. I have this main function, I call it twice, one with nil. This line right here in particular is the one that unpacks the optional. If it's valid, it goes in. If it's not, it doesn't. And the compiler will say like, okay, greeting is defined here. There are safety guarantees to make sure greeting is defined, otherwise it'll complain about the variable. And then I have one on the right here, which actually lets you do switch-based unpacking. And there's a little bit of like ML-style pattern matching here, where I'm taking choice and I'm matching it against the value 1, 2, or 3, or default would be handled in a none case. And since anytime you cast anything to a different type, it comes back as an optional. I expected optionals to be all over. And it turns out they are, but they're not as bad as I was expecting. Optionals are actually pretty thin. Up here at the top, I have the optional sum2 and the optional nil. And the option is the value, and then a single byte that encodes the flag of if it's there or not, or actually the inverse. It's 0 if the option is valid, and 1 if the option is invalid. So, with options being as pervasive as they are, it's nice to see that optional unpacking is the only time you do bitwise anding of 1. So like anywhere there's a bitwise and of 1, wrapping a function block, that's unwrapping and checking the validity of an option. So that was awesome. In this case, I don't have the type marked up properly, V51 is a character pointer, or sorry, a character, and it's the flag for this V52, which so it's saying if in this case it's saying if the option has a value and I want you to retain it, and that's the automatic reference counting that Swift has. So interestingly, the compiler will tell if you haven't handled every case, and it'll inject this bug, which is a UD2 on x86 64, and your program terminates there. We get the illegal instruction, which a UD2 is meant to be an illegal instruction that you can't really handle easily. Not easily, but like it's meant to be unhandled. So my code here is taking 1, passing it to an int, force unpacking it, and printing it. So I pass in 1, I get 1. If I pass in 2, I get a legal instruction. Next up was dynamic allocation and class instantiation. As you would expect from a higher level language, you don't really handle raw memory operations yourself. They're all handled for you. It turns out the way that Swift handles this isn't much different than C++. There are minor differences related to accessing the type and passing it to alloc object. In most, or maybe all cases, you'll use the allocating init version, which is this function allocating init, and that will handle creating, allocating the class and instantiating it, and then it'll pass it and passes the pointer down the inheritance chain to all the inherited from constructors. Interesting though is this V1 type. Swift's allocator cares about the object, which I thought was fantastic, because if you've ever done like heap manipulation or even just debugging of your heap state, you kind of want to know like what object is where and like what type of object is being allocated, and you just have to access the register to get it here. This object is 24 bytes big, and this is decimal scripts, and it's aligned. The alignment mask is 7, meaning it's aligned to 8-byte boundaries. While researching this, I found this awesome comment. This is a declaration for Alex Swift, and it says, at some point soon after return, it will become an invariant that metadata get size will equal the required size. I'm like, wow, a great grace condition. So I was thinking like maybe this data is populated by some other thread, and we could exploit that in some way, play with that non-determinism. But annoyingly, it's actually backed by the default slow malloc. Now there's some to-dos that suggest it will be optimized in the future. So let's wait for that. That'll be fun. Back to our class instantiation example, though. Each class has an allocating init version and the non-allocating init version. And as you'd expect, they just call into their own parents' constructors and allocating constructors. This is super confusing, but all of these return result. So it looks like it assigns it, but it doesn't. It's just X-rays not understanding that the first item, or first member in the structure and the structure itself are the same thing. In this function, in C++, it would be responsible for assigning its own class's v-table. The language, the alloc object actually does it for us. So that's cool because it'll make reversing strict Swift stuff much easier. So I have my initial questions. And so Objective-C is, or I'm sorry, Swift is not like Objective-C, it's not message-based, it's more procedural, it has more devirtualized calls and uses regular lookup tables for its dispatch, just like C++. It's not lazy like Haskell, which would involve like linked lists of hundreds of thunk chains that I actually tried to reverse a Haskell program once. It was print hello world, and on hour 3 I gave up. So the native types that are available are the usual ones. I guess it didn't. So which storage backs the types of each variables? I'll just tell you this one because I forgot to actually put a slide in for it. That stacker heap, it really just depends on the lifetime. Class instantiation is slightly different than C++, and options are not with and. Fun. Last section that I looked at was the Swift ABI. The specific areas I wanted to research were how Objective-C bridging happened, how virtual function calls were handled, and I kind of previewed that a little bit, ownership rules, and then the calling convention. So Objective-C bridging. Bridging is quite difficult to do on the command line, which took me a long time to make this example. I'm having to use Xcode, sadly. Here I created an Objective-C class that implements one method called class method. Class method 1. And you can notice that and I called it in Swift right here. So let obj equals this Objective-C class and then call the method. You can see that Swift actually instantiates the class as a Swift class that wraps it, and then dumps into the Objective-C horrible indirect message-based function call. And if you're not familiar with Objective-C, this is calling this method. It passes a string, a static string that just says class method 1 to a dispatch table associated with this, and it goes through like 8 layers of lookup tables, 8 layers of function calls to look up how this is done rather than just call. So it's nice to get away from that. Here's just the class. It's the minimal example of the class. It prints the string to the log, not even to the program. It gets it out directly. Virtual function calls. So for virtual function calls, they're implemented basically identically as C++. You have a VF table. You look up. It's somewhat opaque as a pointer. You look up an offset into it, and then you call it. I don't have the type figured out or find here. So, it just looks up make noise, which seems to be pointer 13 in the table, and calls it. This corresponds directly with the code here. Next up was ownership. So object ownership rules are pretty well defined, which is one of the reasons it's safe. Swift is full reference counted. ARC stands for automatic reference counting. And everything is derived from a few base types. Every class that hasn't been decayed into native types is derived from a single base class called heap object, which has your type pointer, reference count, and a few bytes of inline storage for smaller objects. And we also have the function mangle names actually understand their own argument ownership rules. And there's a handful more than this, the dead, guaranteed, exploded, and guaranteed exploded. So dead is when the caller doesn't care about the pointer or the argument anymore. Guaranteed is the caller guarantees the lifetime of it across the callee's function call. Exploded is actually dead and exploded. That involves, that's when the structure has been unpacked in the register. So guaranteed is the same idea, but guaranteed when the structure is unpacked across registers. This all works magically, I guess. but this exploded has caused us a lot of issues. So with the calling convention, so I like to say that Swift's approach is YOLO. And this is because it's whatever works best. And if you've ever actually reversed like C++ LTO code and the visibility is set right on the function, it'll reorder the arguments for the calling convention based on whatever happens to be dead or alive at the call site, because it's faster and better. And like, there's no reason why Swift shouldn't do it, but it causes me a lot of problems because it's not always REX, RDX, RCX, R8 for return values, and they might not spoil every register during the call, and IDA and X-rays assume they do. For the Binary Ninja people, I've requested this feature it should go in and figure out what's spoiled automatically rather than X-rays and IDA's single function view. So X-rays doesn't understand it yet. So variables appear out of nowhere and just read from, and then on closer introspection, you end up inspection. Sorry. You end up realizing that the function call didn't spoil RCX. So this is alive across this call. And I clearly had a lot of issues with the calling convention. You have to do this thing. I'm going to show something deep out of the corners of the IDA manual. I asked Chris about this 2 days ago, and he's like unfamiliar with this page. So in IDA, you can tell it that bytes 1 through 2 are unpacked into this register, and it's called this scattered structure argument format. And you actually can do it with return values too. So where Swift returns everything in registers, these 4 registers concatenate. X-rays doesn't really support that, and you have to make your own Swift call, which for every function that exists, you need to mark it as user call spoils these guys. The return value unpacks into RAX, RDX, RCX, and then it also says arguments. This one also works a little better, but X-rays doesn't actually support unpacking into 4 registers for your return value yet. And it makes this reversing much more difficult. So, Swift call. Those were my initial questions for the ABI. So, Swift bridging into Objective-C is seamless. It implements virtual method calls into similar to C++. Class structure are laid out in memory exactly like Objective-C. It seems I missed another slide. The funny thing about the ABI documents for Swift is they are the most definitive documents for Objective-C also. Because there's just like a ABI.markdown file that says this is how Swift is, and since Swift is this way, Objective-C has to be this way. And there's no corresponding document for Objective-C, so you actually want to do more Objective-C reversing. You should read the Swift ABI documents as well. And then the calling convention is whatever the fuck it wants to be. So, getting back to tools, I have been slowly working on a tool. Sadly, it's for IDA and X-rays only, and sadly, it's in Python. I begrudgingly wrote it in Python because it's impossible to compile on a Mac 64-bit X-rays plugin, as far as I'm concerned. So it's called Swift.py. It rewrites the X-rays output for just 4 demangled names, since IDA doesn't have an API to add your demangler. It also annotates IDA with these demangled names, and then does class boundary recovery. In the future, I'm going to do type propagation based on the hexarrays AST, and then maybe witness table recovery, which is an extension of the protocols that it gets annoying at that point. And then I'm also looking to update class dump to support Swift classes and protocols. I have a small demo, and we'll see if the demo gods are happy today. I'm going to say no because my laptop refused to return from suspend earlier. So this demo is super simple. It only shows the demangled name feature. It uninstalls the plugin, launches IDA. We see horrible mangled names that don't matter, don't mean anything. I see the word print in here. I don't know what that means. Separator stuff. There's a Swift release, which is completely unmangled. And then it moves the plugin back in, and we see the names are demangled, or most of them are. And we can see that this is a Swift print specialized to an array, taking a string, and you can slowly read the Swift. In the talk, you may have realized that all of my screenshots, except for the first one, actually already have this plugin applied, because otherwise it'd be really confusing. So, yeah, it applies automatically. It's kind of seamless. I actually had to reverse engineer IDA to figure out how to call this API, because ILFAC was giving me the wrong information. He said that no one had ever tried to do it before, which I don't really believe. And yeah, that's the demo. There's still a lot of work to be done. I still need to figure out, how to handle this calling convention concisely across the whole binary. I will continue this work. So that's my talk. This is me. Are there any questions?
All right, so who is reverse engineering Swift when they go home? It's like, thank God it's not me.
It's not as bad as I expected. It's not Haskell.
Okay.
It's what I had to keep telling myself.
That's a motto I'm going to get tattooed on my chest later today.
Is your tool available online?
If you look hard enough.
That's true for all information.
No, it's not available. It'll come out eventually.
Is there any chance that in the future Swift will be supported on Windows, or
as of I think yesterday, Redstone Beta 1, its latest build lets you put Ubuntu on Windows, and then you can build Swift for Linux, so you can have Swift on Ubuntu on Windows. I think that's your best bet right now. I mean, the Mac rumor says Swift is coming to Android and it will be a first-class language supported by Google. But it's Mac rumors, so I don't know if they have deep ties into Google. They also said Uber was at this meeting, so I'm very skeptical.
I like it. All right, well, thank you very much.